from Idaho. I strive to provide interesting videos about motorcycles, fabrication, welding, electronics, machining, and general creativity. I hope you enjoy. Well, it's getting pretty late in the day. I wonder if the mailman has been by yet. Hello from Idaho. Well, the mailman finally came, and so I can get my mail. Sometimes he comes at 9:45. Sometimes he comes after dark. And so if I'm waiting on something important, I generally have to, or I don't have to, but I generally check the mail too many times a day, which is annoying. So today we're going to do a project that fixes that. Commercially, there's a lot of spring-loaded and weighted things that will pop up when you open the lid. There's even a few that are electronic. They mount in the back and they sense light when you open the lid, or they have a magnetic switch or whatever. But I can't believe they want 30 to 100 bucks for these things. So we're going to make one for a few pieces of scrap and a little bit of paint. So I have measured up my mailbox. It's not especially unique. It's a fairly standard 6.5 by 8.5 by 19. But I do have this pole over here to contend with. This side has the flag that I use to tell the mailman that I have outgoing mail. So the flag, if it comes up here, will have to miss this, and I'll have to get rid of one of my little whirligigs. We get quite a bit of wind sometimes in the spring and fall, so it's kind of cute to have these little flag-based graphics whirligigs. So let's go in and look at the plans. Okay, here's our plans. I took all the dimensions from the street, the mailbox, the size of the mailbox, the size and placement of the post, how high it is above the top of the mailbox, etc. So we have a side, top, and front view. The difficulty here is that the weight can't be too big, or it runs into something down here below this. And the flag can't be too big, or the arm can't be too short, or we don't clear the post. So there's only a couple ways that I know of to get this done. One is to weld something up and try it, and then when that fails, modify it and continue to do that until you get something that works. It's much easier to do that iterative process in a drawing tool that gives you something to scale. And so I've worked out a bunch of scenarios of how big the weight can be, how far up on the mailbox it has to be, how long the arm is, how big the flag could be. And I've come up with this set of plans here. Basically, it bolts to the side of the mailbox with a bolt, some fender washers, a bushing. And you can see that there's a sear plate here on the front, so that when the mailbox opens a little bit, that sear will release the arm and the flag will go up. So let's look at the particulars. Okay, here's the flag. I've decided to pop rivet it on because in my tests, I really did a poor job of soldering 16 gauge to the 1/8 inch arm. And I want the flag to be light because it's way out on the end. And so I just decided that it'd be easier if I just pop riveted it on. But basically it's 3 by 3, except for these couple of little pie cuts in there that don't do anything except add some aesthetics. It's just 190-degree bend, holes for pop rivets. Pretty easy piece to make. Here's the crux of the matter. Here's the weight and the arm. And so the weight is 3/8 inch thick by 3 inches wide, and it's 6 inches long. And I'll tell you how I come to know that that's a good value in the last slide. The arm is 3/4 by 1/8, plenty strong enough to hold up a flag, but it doesn't weigh too much. And then the end is drilled for the pop rivets that hold on the flag. Top view and front view are pretty boring. So you do have to weld 1/8 inch to 3/8, but that's not so bad as welding 16 gauge to 1/8, at least for me. Okay, this page reminds us to pop rivet on the flag. Just included for completeness. Here's the sear plate. It's 1/2 inch by 1/8 inch flat bar. It's got a couple of holes in it for pop rivets, and it just sticks out far enough past the mailbox to hold down the arm. Now here's some important dimensions as well. Here's how to drill the mailbox. If we come back 12 inches and up 5.5, that puts us up high enough on the mailbox that we have room for that weight to swing, but not high enough that we're into the curved part. And then we have to drill the lid as well for the 2 pop rivets that hold on the sear plate. Here's the bolt detail. This shaded light blue is the side of the mailbox. It's sandwiched between 2 body washers, 2 fender washers. A 1/4 inch bolt goes through the whole thing. And there's a bushing here that's captured between this fender washer and that washer. And so the bolt is tight, and this bolt sticks out there and it's rigid. The flag weight has a 3/8 inch hole in it, and it rotates on this bushing. And there's a little extra slop in the sides, so this is 3/8 and the bushing is 13/32. The bushing is 1/4 inch ID, 3/8 inch OD. You can get them in different lengths at various hardware stores, Home Depot, D&B, Ace Hardware, etc. Okay, now we're going to calculate the weight that we need for the counterweight. Now don't panic. I know this page has got a lot of numbers on it, but we're talking about a really simple concept. So before you turn away from this, let me tell you what that simple concept is. The concept is of a teeter-totter. You have a fat kid on one end and a skinny kid on the other, and the fat kid pushes the teeter-totter down. But if the fat kid moves in, now they can balance. And so the distance from the pivot point and the weight on each side is what matters. And so in our case, we've got 3 kids. We've got a flag and an arm on one end of the teeter-totter, and we've got a counterweight on the other. So we need to know the weights of each flag, arm, and counterweight, and we need to know how far away they are from the pivot point. And so in steel, we know that the density of steel is 0.283 pounds per cubic inch. And so if I've got a 1 inch by 1 inch by 1 inch, that's 1 cubic inch, and it weighs 0.283 pounds, or just a little over 4 ounces. And so by knowing the volume of each one of the pieces, we can multiply it by the density and get a weight. So the flag is 3 by 3 by 1/16. So it has 0.563 cubic inches of volume. Multiply multiply that by the density of steel, 0.283, and we find out that the flag weighs 0.159 pounds. Simple, volume times density equals weight. The volume of the arm is 12 by 3/4 by 1/8. And so that means it is 1.125 cubic inches times the density of steel means that it weighs 0.318 pounds. Now for the counterweight, I'm just going to calculate the weight for 1 inch because we don't know how many inches we need yet. So the counterweight is 3 by 3/8 by 1, which also gives us a volume of 1.125 coincidentally. And so it weighs the same as the arm. 1 inch of it weighs the same as the arm. And it weighs 0.318 pounds. Okay, so we now know the weight of each piece. Now we need to know how far away from the pivot point each piece is. And we can multiply those two together and find the torque that each piece applies to the teeter-totter. So the flag is 0.159 pounds, and its center of gravity is 10.5 inches from the pivot, which means it applies 1.671 inch-pounds of torque to our teeter-totter. The arm is 0.318, and its center of gravity is at 6 inches. That's because the arm is 12 inches long, so the center of gravity is at 6 inches, and so it applies 1.910 inch-pounds of torque to our teeter-totter. Now the counterweight's on the other end, but we can add these two together, and so 1.671, 1.910 gives me 3.581 inch-pounds of torque on one end of the pivot. The counterweight's on the other side, and so if we take its weight, 0.318, and multiply it times its length, that's how big it is, and we multiply it times its moment arm of length over 2, that will give us how much torque the counterweight applies. And so if we want, let's say we want them to balance, just exactly balance. So at balance, the weight, the torque applied by the arm and the flag is 0.3581 inch-pounds, and the torque applied by the counterweight is 0.318 times its length times length over 2. So if we we divide both sides by 0.318 and we multiply both sides by 2, we find out that 22.552 is equal to L squared, the length squared. So we take the square root of that and we find out the length to perfectly balance is 4.75 inches. And so any counterweight bigger, longer than 4.75 inches is going to drive that end down, just like the fat kid does. And so in our case, we've got 2 light kids out here on a quite a ways away, and 1 fat kid down here. And so we've got 4.75 inches, will perfectly balance. If we use 6 inches, which is 1 1/4 inches longer than we need, then that's going to drive the flag up, and it ought to drive it up against a snow load, snow landing on the flag, and wind to keep it up during the wind. And so that's why early on in the first page, we used a 6-inch counterweight. And so the only thing really left to do is to cut some parts, weld them together, drill some holes in the mailbox, paint it all up, and wait for the mailman. Okay, by golly, we're done. Got to paint it and drill holes in the mailbox and shorten my bushing down to 13/32. But this goes out and gets painted. Okay, one last little bit of fabrication. We need to shorten this bushing. So I like to set up my parting tool like this. Just use a razor blade and find the edge of the tool. Okay. Now you can go in from there, and you don't need to know the width of your cutting tool or anything. All right, let's see. Those are 10 thousandths, so .1, .2, .3, .4, about 410. That's the way we want to be. It's about 13/32. Okay, that's pretty good. Just a little double check. Yahtzee. Okay, I guess we wait for the mailman now. Good, how are you, sir? As usual, if you like or dislike my video, please select the appropriate button and let me know why. I really appreciate comments and I will answer every one. If you're new to my videos, please select the subscribe and the notification bell to get more videos like this.